Hello everyone. Hi guys. Good afternoon to all of you. I hope you have very good sessions of unsaturated soil mechanics. Hello. Nagesh Kumarji. Hello. So today we're going to address any questions if you have other than what has been discussed in the sessions, video lectures. So far I have received only one question from Malia Chetia. So I'm not really understood whether the teaching was bad or it is well understood. If you have any questions, please let me know. I will address that question also. Apart from that, if you have any, you can type. I'll answer it right away. So if you are still thinking about the questions, let me start a PPT which I have prepared, which contains different topics that are covered in the sessions, different video lectures, and some of the questions that are received in the discussion forum, and a question that is received recently on the Google forum for this live session. Firstly, in the first week, we have discussed introduction and fundamental principles. In that, the 3 lectures are covered on fundamental aspects of unsaturated soil mechanics and its basic principles and phases of unsaturated soils. In the week 2, we have covered equilibrium between air and water phases, capillary phenomena in unsaturated soils. In the next week, we have covered fundamental principles and constitutive relationships related to unsaturated soils and concept of water retention and soil water characteristic curve. And in the 4th week, we have discussed hydraulic conductivity functions and determination of state variables and suction measurement and control techniques. Here we have discussed several laboratory and field measurement techniques that are often employed for suction measurement or control. In the week 5, we have discussed hydraulic conductivity function determination and the theoretical models for SWCC and HCF. And week 6 contains some more modeling aspects of hydraulic conductivity function, fitting of SWCC and HCF modeling, and pedo transfer functions, PTFs. Here, Arya-Paris method was discussed. In the week 7, the flow behavior was discussed, where steady state flow through soils and transient flows. Some analytical methods for transient flows are discussed. And in week 8, the shear strength of unsaturated soils has been started, where the shear strength of unsaturated soils using suction control direct shear test was discussed. In the next week, the suction control traction test and extended MC criterion, Moore Coulomb criterion, was discussed. And the concept of suction stress was introduced in week 10. And in the week 11, we had suction stress introduced, and later on we had volume change behavior that was discussed. However, I didn't put it here. So coming to the question that has been discussed, that has been raised by Dr. Malia Chetia, what are the real applications of unsaturated soil mechanics concepts in practice with some real case applications? Generally, this question has been asked by many, in fact. But the one thing we need to understand is that without having applications, generally researchers do not spend their money, time, etc. There are real applications that are encountered with unsaturated soils. So the behavior is very difficult to understand. Therefore, a lot of time has been invested. Time and money has been invested on understanding the unsaturated soil behavior. So that is how the unsaturated soil mechanics concepts have been evolved. So earlier, this particular concepts have been widely used in soil science, that is in agriculture and other fields. However, later on, those concepts have been taken up in soil mechanics or engineering, especially the shear strength topics and consolidation. These aspects are not completely understood in soil science because it is irrelevant for them. So to understand the shear strength behavior, consolidation or settlement behavior of unsaturated soils require considerable effort in properly understanding these things. So these aspects were understood because there were real applications such as rainfall induced slope stability. That is a very damaging thing in many parts of the world during the monsoon seasons. That has been discussed in the introduction chapter or introduction video lectures, and erosion control for the riverbanks, etc. And another thing is the design of nuclear waste repositories. Some of the nuclear waste repositories that have been discussed since 80s in USA, like Nevada and Las Vegas. They wanted to, in Yucca Mountains, they wanted to dump these spent fuel wastes, and that has been in discussion since 1980s. So last 30 years, a vast improvement on understanding of this unsaturated soil behavior has taken place. And some of the real case applications that have been successfully used, I have listed 3 of them here. The mega south to north water transfer project in China. This has somewhere started in 2009 to 10, so about 10 years ago. So this is successfully implemented because when this was made, artificially the water was pumped towards the north from south. While constructing this canal, they encountered around 300 kilometers expansive unsaturated soils. That was very difficult for them to construct. So here, real-time tests were conducted using the artificial rainfall-induced slope instability tests, etc., to understand the stability of the canal sides. So this was successfully implemented, and this was completed on time, in fact, on or before time, in fact. So here, a lot of unsaturated soil mechanics concepts have been used and also evolved during this construction process. Secondly, the design of nuclear waste repository, just I discussed, because this is a very important thing. Exact location of these repositories may not be revealed by different countries, but definitely underground repositories using bentonite backfilling is seen as a viable solution by many countries, and they have accepted it. So therefore, there's a lot of research that has been taking place in this direction. So here the bentonite is compacted at very high densities in completely aerated state. So when it comes in contact with the water from the surrounding saturated rock mass, so the swelling behavior and the flow behavior are very important. So the hydromechanical aspects of these unsaturated soils is very important. So that is how a lot of research is going on, are taking place in this direction. The rainfall induces slope instability stability projects are many in US, especially by real-time monitoring the suction and water contents. They've been trying to address how the factor of safety for the slope stability are changing. This is done in real time by many researchers like God, Lu, and Lycos, and many others. They've been publishing regularly on AEC journals their field projects by real-time monitoring these data and understanding how the slope stability things are changing, are varying. I hope I addressed you, Malia. If you have any questions, please let us know. So apart from this, there are a few questions that are asked in the discussion forum. Our TAs relentlessly addressing these questions time to time. So such questions, how some of those questions are mentioned again here. One of the questions is in consolidation test, why soil samples submerged in water? Because in normal design aspects, so far we've been discussing the saturated soil or understanding saturated soil behavior for conservative solutions. So if it is a fully saturated soil, then the complexity of surface tension, all those aspects are not there. So it is very simple to address this. So generally the design is done using this so that you maintain good factor of safeties. So generally our consolidation tests are done with fully saturated state. So we submerge the sample in that. So how the permeability is correlated to landfill liner design or earth dam design? The permeability generally in landfill liners or earthen dams should be low enough to contain contamination in landfills or water in earthen dams. So hydraulic conductivity should be maintained as low as possible. That's why we use clays, either bentonates in landfill liners or earthen dams. Clay core is used very often. In consolidation test, if a soil sample is placed between porous stones, how the water drained uniformly from top and bottom porous stones. So here there's a gradient that is developed when a consolidation test is conducted. Two porous plates are placed on top and bottom to simulate a double drainage condition, which is often encountered in the field, or also to accelerate the consolidation process. So we place the load on this. Here there's a maximum gradient that is developed. Here, if the length of the soil sample is L, which is generally about 6 centimeter or 60 mm for our consolidation tests, which we often use, and this is about 30 mm. So when you apply a load of say 25 kilopascal, sorry. So when we apply a load of about 25 kilopascal, which generates a head of, so applied pressure is sigma divided by gamma W about 10. So about 2.5 meter head is generated. So there's a length of about 3 mm, sorry, 30 mm, that is 3 centimeter. So this much of hydraulic gradient is generated. So when you have this much of hydraulic gradient, so the water within the soil mass moves towards these boundaries, in fact. So it moves towards the boundaries because the gradient is maximum. So hydraulic gradient is maximum towards the boundaries. So therefore the water moves towards the boundaries. And soil sample is so thin, that is 6 centimeter, or the maximum path length is 3 centimeter. Therefore, the available path length is compared to the head is so minimum that it uniformly moves towards both the porous stones. I hope you understood it. So there's one question from Nagesh Kumarji on why direct shear box is not used for cohesive soils. This is especially to something to do with controlling the drainage. In our shear box test, we do not have a control on drainage because in triaxial tests, we have proper control of drainage and we can control the amount of water that can come out. But in direct shear, we do not have any control and cohesive soil should not be used. So we use, generally the design, the shear box is designed for dry sands. However, we've been using it for, so generally the direct shear box is designed for dry sands, for testing the shear strength of dry sands. But often we've been using it for clays or cohesive soils and other soils, and that with some degree of water content or something. but that is not designed for actually for that particular condition. So if you can properly control the drainage, if water, all the excess pore water pressure drains out during the shearing process, so that you shear it so slow, then possibly it could be used without much error. So if you don't have much questions, I'll switch to the presentation. Yes? One more question. Okay.
Should I repeat the question?
Yeah, please. Okay. How to prepare cohesionless soil samples for tractional test? So this is a standard practice. You have one rubber membrane which is used for preparing the samples. Those are cohesionless samples like sands, etc. This is a very standard technique that is used, and all basic soil mechanics textbooks are, your Indian standard codes also emphasize on how to prepare the cohesionless soils or sands for tractional tests. You have a rubber membrane which holds the soil. I hope I answered Ranveer Sagiji. Okay, let's move on to the PPT again. Oh, yeah, sorry. This hydromechanical behavior I just explained, in fact, earlier during the discussion on nuclear waste repositories. The hydromechanical behavior is nothing but the hydraulic behavior plus mechanical behavior. Hydraulic behavior is the flow behavior through unsaturated soils, and the mechanical behavior is either swelling or consolidation. It is under the load application how it behaves. So hydromechanical behavior emphasizes on hydraulic behavior or flow behavior under the mechanical aspect. So it's a coupled analysis that is often done. So in tunnel seals and shafts, etc., because the bentonite are sealed there, so you require to understand the hydromechanical behavior of these bentonites. When we, this is from Shruti MR, when we freeze water, it expands and may form tension cracks in the soil structure, especially when we try to maintain the volume constant. In that case, how we can say that the soil structure has not been disturbed after freezing and sublimation process? So this is a very good question, Shruti. In fact, when the volume changes, volume of water changes, the structure also slightly changes, in fact. So that is assumption we take into account. We do not take into account, but we assume that it does not seriously cause any structural change within the soil mass, and then we use it. Especially when you have compacted soils. When you have a compacted soil, like compacted to very high densities or consolidated samples, when you freeze dry it, the changes in the pore volume or the pore water volume does not significantly cause or damage the structure of the soil. If the soil is in slightly loose condition, then if you freeze dry it, you get often powder. You do not get the structure intact. So that is the reason. So at a very high density, or when the soil receives good enough effective stress, then it has sufficient strength to withstand the structure, then we can freeze dry it. Fine. So this is by Prudvi Chandra. How moisture content of soil sample will be same at after reaching equilibrium? It would be higher than the previous measured moisture content value. I think this question is with respect to the vapor equilibrium technique using salt solutions. When you have salt solutions, the soil is generally exposed to the salt solution vapors, so that there is an equilibrium. Once the equilibrium is reached, the same suction that is exerted by the salt solution will have in your soil mass, so that you can use this particular suction value to understand what is the corresponding moisture content or to establish the entire SWCC. This is one of the data points. Here I meant that once the equilibrium has reached, once the moisture transfer has occurred within the soil mass from the salt solution vapors, we need to generally find out what is the suction value of the salt solution using WB4. So generally this is done. So at the end of the test, at the equilibrium, we generally measure what is the suction value of the salt solution, and we use this corresponding to the suction of the soil. Generally, depending on the initial soil condition, if the soil suction initially when it is placed in the environment of soil vapor, salt vapors, if it is suction is too close to the salt vapor suction, then the significant change in the suction will not occur in the salt solution. Therefore, initially based on the prepared one, we can directly use it. Fine. So if the soil, I'll give an example if you don't understand it. If you take a air-dried sample which is compacted to very high densities and which has very high suction, and salt solution you are taking something like KCl at probably 2 molar or something, it may be around the suction may be around 2 MPa or something. So clay sample compacted, when it is compacted to very high density, it may have a suction of about above 500 MPa maybe. So when you have such a huge variation in the suction, definitely there's a change in the salt solution concentration at the end of the equilibrium, at the equilibrium. Otherwise, if both are having similar values of suctions initially, then the suction values would not change in the salt solution significantly. So generally the practice is at the end of the equilibrium, we take the salt solution, we measure the suction in WB4, and we incorporate this value in the SWCC data. Fine. So with Jayalakshmi, it is mentioned study flow through soil for saturated condition, not for saturated soil. Since the study flow cannot happen in dry condition, it is possible in fully saturated or partly saturated condition. Please clarify. That is true. In fully dry state, when the soil is in fully dry state, there's only vapor flow that takes place. If you have partly saturated soil, that is some moisture is available, that too this moisture should have continuous channels that are established within the pore structure, then only flow takes place. And then you talk about the steady flow. Otherwise, if there is a discontinuity flow, first of all, flow doesn't occur. Flow of water doesn't take place. When flow of water takes place through the soil, it can be steady state, having an unsaturated soil. That is what I meant. Your question is valid. That in fully saturated condition we can have steady state flow. We can have steady state flow even in partly saturated soil. Fully dry state you may not have, because you will not have continuous channels established within the soil. Thank you. Then, so these are the questions. If you have any more questions, I'll address. I hope there is some clarity. Randir Sagiji, you're welcome. Nageshji and yeah. So in case if you have no questions, then those who have at least communicated or those who have asked questions, probably you can introduce here. You can type where you are from. You can introduce yourself. your college and sir, course was really useful. Previously, I thought soil mechanics. No, that's okay. You can retype it. Hi, Abhay. Yeah, that was the initial understanding. Soil mechanics initially is thought for only completely dry soil and for purely saturated soils, when the water component is not considered. But when Terzaghi is introduced, Terzaghi has introduced the water into the soils, and after that it is for only saturated soils. Then later on, the Bishop and other people have worked to address the shear strength aspects of unsaturated soils. Abhay is from SOE CUA Kochi. Nice to know. Nice to know. Randir Sagiji, you are from Rajiv Gandhi University. RJUKT, Basar, Telangana State. Okay, nice. So we'll end the session. If you do not have any questions, so I hope you have registered for the exam. If you haven't, you can register. Vineet Karnati from NIT Warangal. Could you please explain the difference between the intergranular pressure and effective stress? So the effective stress is generally taken up as the forces between the granulars divided by the whole cross-sectional area. Intergranular pressure is the forces at the intergranular contact points divided by the contact area, that is very high. So intergranular pressure is not relevant to us. Effective stress is relevant to us. Intergranular pressure is close to infinity because the contact point or contact area is close to zero. Effective stress is the intergranular force divided by the whole cross-sectional area of the soil. I hope it's clear. Any questions? Then we'll push off. So all the best with your exam. Take care. Thank you.